Welcome to The Explainer. Today, we're diving into an invisible force that, believe it or not, powers our entire modern world, the magnetic effect of electric current. So, to kick things off, let's start with a question that honestly baffled scientists for centuries. What in the world does a battery have in common with a magnet? I mean, at first glance, they seem like they're from completely different planets, right? One is the power behind a lightning strike, the other is what keeps a compass needle pointing north. And for the longest time, yeah, the official answer was absolutely nothing. Seriously, electricity and magnetism were seen as two totally separate forces of nature. They were in different textbooks, studied by different people, and as far as anyone knew, there was just no connection. But that all came to a screeching halt in 1820. And get this, it happened by total accident. A physicist named Hans Christian Ørsted was in the middle of a lecture, just demonstrating a simple electrical circuit, when he noticed something, well, something really weird. Here's what he saw. Every single time he switched on the current, a magnetic compass just sitting on the table nearby would twitch. Its needle would literally jump and point away from north. And that's when the light bulb went off. He realized the electricity moving through the wire was creating its own invisible force, a magnetic force. And this incredible phenomenon, we call it the magnetic effect of electric current. And this is the absolute key for our whole explainer today. It's the moment we learned that electricity and magnetism aren't separate at all. They're really just two sides of the same coin. Okay, so we've established that a current creates this invisible magnetic field. But how can you possibly wrap your head around something you can't even see? How do you predict what it's going to do? Well, this is where physicists got really clever. They came up with a brilliant tool to help us visualize this force. They figured, hey, if we can't see the force itself, let's just draw a map of it. And to draw that map, they used something called magnetic field lines. Think of them like a weather map, but for magnetic forces. They show you both the direction the force is pointing, always from a north pole to a south pole outside the magnet, and how strong it is. The more bunched up and closer together the lines are, the stronger the magnetic pull. All right, so now let's take these rules of the road and apply them back to Ørsted's big discovery, a simple current-carrying wire. So if you could somehow put on a pair of magnetism goggles and look at a straight wire with current flowing through it, it wouldn't look like a bar magnet. Nope. Instead, you'd see these perfect concentric circles of force just wrapping themselves around the wire. The big question, though, is which way are those circles spinning? And for that, there's this awesome little trick called the right-hand thumb rule. It's super simple. Just imagine grabbing the wire with your right hand. Point your thumb in the same direction the current is flowing. And voila! The direction your fingers curl around the wire, that's the direction of the magnetic field. Okay, so straight wires, we got this. But things get way more interesting when we start messing with the shape of the wire. What do you think happens if we take that straight wire and bend it into a nice, neat loop? Well, that same rule applies to every single point on that loop. But now, something really cool happens. All those little circular fields start to add up and reinforce each other, funneling together to create a powerful, combined magnetic field that flows right through the middle of the loop. And that is the crucial point here. By shaping the wire, we can actually control and concentrate the magnetic field. This is the moment we go from a cool science curiosity to an incredibly powerful engineering tool. You know, if one loop is good, what about hundreds of loops packed tightly together in a coil? Well, that's what we call a solenoid. And when you run a current through it, it generates a magnetic field that looks almost exactly like a classic bar magnet. The real magic, though, the secret sauce, is what happens inside the coil. Because all those fields are lined up and packed so closely, the magnetic field inside becomes incredibly strong and, just as important, almost perfectly uniform. It's like a stable, predictable magnetic environment that we can control. Okay, now for the final game-changing step. You take that solenoid and you place a soft iron core inside it. That's just iron that can be easily magnetized and demagnetized. The solenoid's magnetic field turns this core into a temporary supermagnet, making the whole field thousands of times stronger. And just like that, you've created an electromagnet. And this table right here illustrates the key advantage perfectly. Unlike a permanent magnet you stick on your fridge, which is always on and always the same strength, an electromagnet is completely controllable. You can make it stronger or weaker just by changing the current.
You can reverse its north and south poles, and, most importantly, you can turn it completely on and off with the flip of a switch.
This precise control is exactly what makes the magnetic effect of current one of the most world-changing discoveries in history. It allows us to do something truly remarkable. Okay, let's connect the final dots. So far, we know for a fact that a wire carrying a current produces its own magnetic field around it. Check. This leads us to the final, powerful consequence of that discovery. What happens if you take your current-carrying wire with its own little magnetic field and you place it inside a different, larger magnetic field, say between the poles of a strong magnet? Well, those two magnetic fields can't occupy the same space without affecting each other. They're going to push and pull against one another, and this interaction results in a real physical force that pushes the wire, causing it to move. And that, right there, is the ultimate payoff. We've turned electricity into motion. This single principle is the foundation of the electric motor, which powers everything from giant industrial cranes that lift cars with electromagnets to the tiny motors that make your phone vibrate. And this leaves us with a final thought on just how profound that accidental discovery in 1820 truly was. It unlocked the ability to transform electrical energy into mechanical work, literally setting our modern world in motion. Thank you for joining this explainer.